Road to Olympiad.
Welcome to RTO. Consider the following problem. Prove that if the polynomial px is equal to anx to the power of n plus an minus 1 x to the power of n minus 1 until a0 with integer coefficients have p0 and p1 are both odd, then the equation px is equal to 0 has no integer solutions. The information p0 and p1 are both odd here seems to be redundant and doesn't seem to be helpful in the proving. However, there's a smart way of making use of the informations. In fact, instead of 0 and 1, it can be any even and odd numbers. Pause the video if you'd like to give this problem a try, and keep watching to learn how to solve it. To solve this problem, we start by letting p and q be two integers with the same parity. That is, p and q are either both odd or both even. Consider pp minus pq. This gives us these expressions, which we can simplify to this one. Notice that a0 is vanished here because they cancel out each other during the subtractions. Notice that we have a bunch of power of p minus power of q over here. By using the identity, we can write p to the power of k minus q to the power of k as a multiple of p minus q for any positive integer k. That is to say that we have each of the term in pp minus pq is a multiple of p minus q. Or pp minus pq is divisible by p minus q. Recall that p and q are of the same parity, so their difference will be an even number, and thus we can rewrite this statement as pp and pq is even. Having these informations, we can now finalize our proof. Consider the case where x is even, then we have px minus p0 is even because x and 0 are both even number. And since p0 is odd, it's follow that px must be odd number if x is even. By using the same argument, if x is odd, then we have px minus p1 is an even number because again x and 1 are both odd numbers. And since p1 is odd, we have px is odd as well if x is odd number. Combining both the cases, we have px is odd for any integer x. And this tells us that px is 0 has no integer solutions because for any integer x we must have px is an odd number which cannot be 0. And this marks the end of the proof. Post in the comment below if you have any thought on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.